Okay, good. So anyways, so if you're really keen on seeing the homework, especially if you're keen on submitting the homework, then you must be enrolled on this thing. So, but let me know if you have troubles for that. Okay, so now, we started talking about ergodic theory last time. So today we will keep talking about that, and in fact, we will prove one of the basic ergodic theorems. There's 3 of them, and so let's recall what is the setup here. So the setup is the following. So we have a measure preserving system. So what is a measure preserving system? So it's four objects, but well, one usually, maybe even 2 of them sometimes are hidden, but there's X. X is a probability space, a measure space. Okay, measure space comes with the sigma algebra, which usually will be implicit, or most often would be the Borel sigma algebra if we start with the metric space, so it's not going to be that problematic. And then we have a measure which usually we might denote with P, so this would be a probability measure. And then a map T, and so T would be the dynamics, or sort of the time evolution. And again, what is T? T is a map from X to itself. And roughly speaking, it is, X, you start with a point X, and X represents a state of the system today. And then T of X represents the state of the system at the next time interval. So for instance, tomorrow. And okay, where does measure preserving come from? It's because we also need to be that the measure is preserved. So if we want to write it in a sort of shortened notation, you say that the push forward of P under T equals P, which basically says, which is equivalent to say that for every A in your sigma algebra, the probability of A is the same as the probability of the pre-image of A under T. So in general, for any event that you can think of in your system, the probability that this event is true holds today is the same as the probability that this event holds tomorrow. However, of course, this is only in probabilistic terms. So you see the points that belong to A today, well, they definitely need not belong to the same set tomorrow. But on average, over the whole universe, then the measure of this set and the measure of that set is this. Of course, we can talk about invariant sets, which are sets where really A equals to the inverse of A, and so these are also very important, but much more rare. Okay, and so this is the setting, and then, well, the other thing that we discussed is that the way we probe the system is using so-called observables, which are just functions on your space. And basically, the only thing that you require is that they are measurable with respect to this sigma algebra. So, of course, the preimage of a Borel set in R would belong to this sigma algebra. And again, the intuition is that you cannot maybe see the system itself, but you can tell some property of the system. So f of x tells you some number that tells a certain quantity of the state where you are. Okay, very good. So now, yeah, we kind of didn't see examples, so I think it's useful to see some basic examples. So the first example that people deal with in ergodic theory, even though not so closely related to the theory of random walks, is you take just S1, so R mod Z, So this is, of course, S1. So, and you take f of x to be a rotation of the circle. So x plus alpha mod 1, where alpha is a priori could be any parameter. So, and what is the measure here? Well, in this case, we can just take P, the Lebesgue measure. And in this case, it's somewhat intuitive that when you take, you know, okay, let's write the circle like this. So it's like you think of 0 and 1 are joined to each other. So you take R and you identify 0 and 1, so you get a circle. And then, yeah, simply, and you take a subset, some subset A, then you rotate the set by alpha. So this is maybe A plus alpha. You see that it's pretty obvious that the measure of A and A plus alpha is the same. And actually, but however, we have to take the pre-images. So really, technically, what you want to say is that the probability of A is the probability of T inverse A. But in this case, this is the probability of A minus alpha. So it's just like you do the opposite rotation. In this case, everything is this map is a bijection, and so there is not so much of a problem. And in fact, you see, it does not even depend on this parameter alpha. Even though dynamically, the dynamics of a rotation depends very much on what alpha is, right? Because in particular, if alpha is rational, you have one type of behavior, and if alpha is irrational, you have a very different type of behavior, right? So note that for alpha rational, well, there exists some Q such that for every x in S1, the Qth iterate of x equals x. So some power of T really is basically the identity, and every point is periodic of the same period, right? So if alpha is 1/2, just if you do it twice, rotation of half a turn, if you do it twice, you get the identity and so forth. And for any rational, well, you can choose Q accordingly. But if alpha is not in Q, well, the dynamics is really different. So in fact, for any alpha, for any x in S1, well, the orbit of this, sorry, Tn for n, is dense in S1. But at least from the point of view of being measure preserving, they're both two cases, even though dynamically they're pretty different from each other. They are the same in the sense that they are both preserving the Lebesgue measure. Okay, so another example that is really famous in yes, x is an observable here, like is a function from a circle, right? Is a function from a circle to R. So for instance, theta would be an example. The angle would be an example. Yes.
So your rotation is that, but what about the dynamics?
Oh yeah, I think, sorry, in terms of notation, you're right. So you're right. Sorry. Yes. Other questions? Oh, yeah. Okay. Yeah. So now, so here another example would be if you take still your space to be the circle, and again we can take P to be the Lebesgue measure, and this is invariant under a different type of transformation, which is T of x equals 2 times x mod 1. So this type of dynamical systems is extremely different from either this or this. And in fact, it's not really completely obvious why this is measure preserving. You have to think about it slightly. Because you see, what is this system doing? So, okay, let's say again with 0. Well, you see, like you take a set like this of certain angular, angular width. And when you apply the map, so if this is A, when you apply the map, well, the length doubles, right? So T of A is way bigger. This is T of A. This should be 2 times theta. So this map is expanding. The derivative is bigger than 1 everywhere. But still, the reason why this is measure preserving is because we don't look at the forward image, but we look at the backward image. We look at the pre-image. So we check. So let's check that probability of T inverse of A equals probability of A for every A. Well, the sigma algebra is generated by intervals, so we can just check for intervals. So if A is an interval, so let's say an interval between A and B. Let's draw this graph as a graph, like the sort of like as a function. So 2x, so you have the x and the y coordinate here. So clearly 2x is just a line from 0 to 1/2. And then from 1/2 to 1, well, you have to shift this line down by 1. So the graph of the map looks like this, which corresponds to saying that geometrically, the first half of the circle goes to the whole circle, and the second half, the bottom half of the circle, also maps to the whole circle. And so now if we take a subset AB, and you took at the preimage as well, each preimage has half the length, but there are 2 of them. So it kind of works. So you see, if you take preimage, you have this guy and this guy. So you have, so this is A over 2, B over 2. So this is one of them. Okay, maybe closed again. And the other one is A over 2 plus 1/2, and B over 2 plus 1. And so this is easier. This is clear that T inverse of A is the union of 2 things. And so it's like A over 2, B over 2. So this is one interval, and then it has A over 2 plus 1/2, B over 2 plus 1/2. And so clearly the measure of A is B minus A, which is twice times B minus A twice, which is this guy and this guy. They both have measure B minus A. And clearly you can replace this by times D. For every integer D is the same thing. So here's the exercise. T of x equals D of x mod 1 for any D bigger than 1 in integers is measure preserving for the Lebesgue measure. Simple. Even though it's even more expanding, 3 times x, 5 times x, 200 times x. Yes?
Is this like an if and only if D is an integer?
Very good question. This is one of the homework problems. So you could, in principle, look at, exactly. You could look at a different slope. It's a bit more of a problem in the sense that when you wrap around, you don't cover the interval, and the interval is not covered evenly because there is a little bit, some piece at the end that is covered only by a fewer of them. So it's a bit trickier. So, but this is exactly one of the. Yes. Okay, so, but also again, so this type of dynamical system, just for general culture is really, really different from this one. So in fact, in this case, not all points behave in the same way. In this case, there are points that are fixed, for instance, 0. But there are points that have dense orbit. So there are points, here's another exercise, x, such that Tnx is dense. So not all points behave the same. However, what is true is that periodic points, so points where the orbit is a cycle, are dense. So this type of system is a very, very nice system from the point of view of dynamical systems, because indeed, even though there are periodic points, but the system has a lot of expansion, and this expansion tells you something good about it, that, for instance, these periodic points are dense. So there are orbits that are, not close enough, they're dense, but they can be approximated by periodic orbits. And so this is very nice. Okay, then questions? Okay, so however, yeah, the example we are really interested in for this course.
Sorry, I'm thinking.
Yes.
Yeah, like I'm thinking this is more similar to maybe a surface group's action on its thermal boundary.
Yeah, correct. Yeah, that would be that would be correct. Yes. So yeah, so let's go. Yeah, so actually, this what you're studying in this class is something somewhat similar to this example, but in a symbolic setting. So the next thing is a Bernoulli shift. So what is the Bernoulli shift? Well, we take an alphabet A of symbols, A1, AR. So these are some finite set of symbols, for instance. And we look at X to be the set of infinite words. So infinite words, so each X is Xn, and Xn belongs to A. So this is the set of infinite words in this alphabet. And what is the dynamics here? Well, the dynamics here is a shift map. So T is the shift map. So T of a sequence Xn is Xn plus 1. And what is the measure? Well, there are many measures that work here, but okay, when I say Bernoulli, I mean the following type of measure. So you pick some vector of weights P1, PR, such that these PIs are, well, let's say positive, or even if it's 0, okay, you can forget about that. And the sum is 1. And then we can define a measure on this. Well, kind of obviously, it's kind of the idea that you're picking one element between A1 and AR, and according to the weight P1, PR. So in general, when you have such a system, we define a cylinder set C of, when you have a sequence, so of symbols. So let's call it, let's call it B1, BS. So these are S symbols. So BIs are from the alphabet. So BIs are from the alphabet. And what is a cylinder? Well, it's just a set of X in the space. So the set of infinite sequences such that Xi equals Bi for I less than S. So these are just the set of sequences that start with this. Finitely many options. So you see an example would be if if A is A, B, C, D, and then we can say, okay, C of A, B, well, means a sig X, which is A, B, and then you can do whatever you want. Okay. And then obviously it's kind of natural to define now the probability of this, of a cylinder, C of B1, Bs by taking, okay, P, you see P of B1, so let's say it's P related to the, it is the weight related to this one. Yeah. P of B1, P of Bs. And right, so for instance, yeah, you can take, just to say as a probability vector, we can take, I don't know, 1/2, 1/4, 1/8, 1/8. It should be 1. Right? And so here that you will want the probability of C of AB here. Well, it would be the probability of A times the probability of B, which is 1/2 times 1/4. This is the classical. I mean, it tells you that it's the way to formalize the fact that you have just a classical set of, I don't know, a die with R faces, and each face has a probability P1 to PR to be chosen. So this is a very simple system, but in fact, the system in disguise lies behind a lot of math. In fact, yes.
What space are you defining probability on here?
Yeah, I'm defining this probability on the space of infinite sequences. Yeah. Yeah. And I'm saying that since, in fact, the sigma algebra of, well, I haven't defined the topology yet, but we could take the sigma algebra generated by the cylinder sets, let's say, which in fact, for the usual topology, those would be Clopin sets, so it would be fine. And you can just, you define the probability on each cylinder set, and then this extends uniquely to a probability on the whole space. And okay, so maybe we can just check. You can just check that this is shift invariant. Well, how do we do that? Well, we take the probability of P inverse of a cylinder set. So you have a cylinder set generated by B1, Bs. And so you see T is shifting of one coordinate. So what is the preimage of a cylinder set? So if I fix, if I say, okay, I take the cylinder set where the first letter is A, the second letter is B, and I take the pre-image by the shift, what is the set that I get? Yeah, it's a union of cylinder sets where we don't, the first digit is not specified, could be anything, and then the second and the third are those ones. Yeah, exactly. So this would be, the sum, because they are disjoint of the probabilities of cylinder sets where we have a new letter, which is I don't know, let's call it A, B1, Bs, like this, and then A could be any letter in the alphabet. And so here it's clear that what is this thing? So it's the sum over A of PA times P B1 times P BS. And so this does not depend on A, so we can take the sum of those guys, and this is a probability, so this is 1. So this is PB1 PBS, which is probability of the original cylinder, CB1 BS. Yeah, so this is not that complicated, but again, the system is really important to have it in your mind, because it underlies a lot of our discussions. In fact, the system is very closely related to the SA doubling map, if you think about it. So why is the system very closely related to, say, the map X goes to 2X mod 1? If I have a sequence, the law of large numbers is the next step. But what about really? I'm saying I have the following system. I have our system, which is X, which is I have the following system. I have our R mod Z with the Lebesgue measure. Forget about the sigma algebra, so it was the Borel. And this is the map T of X equals 2X mod 1. Can I express this map as the shift map on certain symbols? Yeah, exactly. So if you think of binary expansions, right? So you can take the following. You can take all the sequences in 0 and 1. Let's say indexed by like this. So this would be infinite sequences, 0 and 1. And you take the measure that is 1/2 and 1/2 on each number. So probability of 0 is 1/2, probability of 1 is 1/2. And here we take T equals the shift. So I claim these two systems are almost the same. What does it mean that they're almost the same? Well, there is a map. So in fact, there is a so-called semi-conjugacy. So definition, semi-conjugacy between two systems, X, A, P, E, and another system, Y, B, I don't know, Q, S is, what is it? Is a measurable map, is measurable map pi from X to Y, such that it commutes with the dynamics. So pi composed with, so you have the following graph, diagram, right? So the dynamics T is on X, so the dynamics S is on Y, and there is a map pi from one to another, which commutes with the dynamics. So meaning that, you know, if you do T and pi is the same as S and pi. Sometimes people want this to be surjective. Yeah, I mean, okay, in the measurable category, surjective really is not the best thing. So maybe you want to say that the image is full measure, but okay. But in any case, so what is the semi-conjugacy? Well, again, if we have a set of sequences, you can map it to S1, we call R mod Z, by taking the binary expansion. I mean, from a point here, you can take a binary expansion, and you get a sequence. And from a sequence, you can take the series, and you get a point. So here's the map. The map is pi from X, Xn to be what? Well, this is the sum of xn to the minus. Okay, it depends where we start. Let's say we start from 0, I think, then probably like that. And so you can check that if I shift the sequence, here I can apply the shift map. And here I can apply the map S, which is just S of x equals 2x. Now, here's a question. Here's this map an isomorphism between these two dynamical systems? What do you think? Do you think these two dynamical systems are isomorphic to each other?
What does it mean?
It's a good question. So usually, right, what does it mean in math to have an isomorphism? Well, many ways you could say that there is an isomorphism and such that its inverse is all. You have a semi-conjugates one way and the other, and the composition is identity, for instance, right? So, well, whether these two systems are isomorphic, I think it depends. Yeah. So where is this map? Is this map bijection? The map from space of sequences to numbers, like from binary sequences to numbers, is it a bijection? No, right? Why? Because pi of 0.01 forever, right? This is the same as pi of 0.10 forever, right? So these are the same number. So pi is not injective. It's not. Yeah, pi is not. It's not injective. However, this really depends on the category in which you are working, because where are these exceptions? Yeah, all these exceptions are countably many, because the only thing that could happen is that you have a word and you put this one on top, the one word and all the ones, right? So this is always what happens. It's the same as you change the last thing on the word, right? So let's call it like this. W01 is the same as W101. So these are the only exceptions. So W is a finite prefix that you can put on both cases. So what it turns out is indeed that it's only not injective on a set which is countable. Right. So here's the upshot. The upshot is, but the set of exceptions is countable. And that's in fact related to the fact that whenever you have a numeration algorithm, so from a number you want to produce, say, the base B extension, well, there has to be some choice at some point whether you choose this representation or this representation. But that's the only thing that could happen. So what is the option is, it depends on which category you're working on. So if you're working with continuous maps, like you could, but it's not what we're doing in this course, these two systems would not be isomorphic. So because pi does not have a continuous inverse. So note the following. So pi is continuous and not injective. Okay, it does not have a continuous inverse precisely for this reason, because so if you're in a topological in the field of topological dynamical systems, which would be the same thing except the maps are continuous and the spaces are topological spaces, then these two systems will be different. These are as more points. However, In the measurable category, it is it is an isomorph. It does have a measurable inverse. And the measurable inverse is you take from a point, you take its binary sequence, and okay, you say, okay, I'll choose the one which always ends with 0 in case I'm in doubt. I'm saying that the measurable inverse would be, we can write it. So let's call it I don't know, P, something P from R mod Z into 0, 1 to the n, where what is the inverse is, okay, P of a point X is the only binary sequence representing X that, for instance, does not end in infinitely many ones. So in case you're in doubt that there could be two options, you forget, you never choose this one, you choose the other one. It doesn't matter, you could choose, everything is up to this countable set which has measure 0 in either case. Right, so we have that pi composed with P equals the identity, and P composed with pi equals the identity. Well, up to measure 0 sets, up to measure 0 sets. So as an upshot is these systems are isomorphic in this as measurable dynamical systems, even though they are not quite isomorphic as topological dynamics. So this tells you that you're losing some information if you go into when you do ergodic theory rather than just topological dynamics. Yes? Yes, okay, I didn't specify, but okay, so the circle has a topology that you all know. So for okay, let's recall. So we want to say that in general, whenever you have a space of symbols, so let's say a to the n, where a is a finite set, is a metric space, in fact. Defining in the following way. Well, if you take two sequences, I look when are the sequences different. So you start from the beginning, you compare the first digit with the first digit and second digit with the second digit. At some point, if the sequences are different, there has to be a point where they are different. And so that's what you do. So you define D of sequence xn and a sequence yn to be, okay, now you can choose some number. Let's say 2 is one option, minus the infimum of k, such that xk is different from yk. So in this case, right, and you see that this could be infinite, infimum could be infinite only if the two sequences are indeed the same, that you get 2 to the minus infinity, which we define to be 0. So this is a metric. And so it induces that topology, which is just a Cantor set topology. It's like, it induces the topology where cylinder sets are Clopin sets indeed. So it induces a topology on this shift space x equals a to the n, so that, well, x is actually compact. It's totally disconnected, meaning that the connected component of a point of a point is just the point itself, and with no isolated points. And so we know that is the characterization of a Cantor set. So X is a Cantor set, it's a homeomorphic to the classical Cantor set. And yes, and also for any finite sequence, for any, you see, finite sequence B1, Bs in A the power S, the cylinder set like this is both open and closed. So the picture is really like a classical Cantor set, right? So if you look at a ternary Cantor set, how can we think of the ternary Cantor set? Well, we know that the digits in base 3 are either 0 or 2. And so if we specify 0 at the beginning, we get the first interval. And if you specify 2 at the beginning, you get the second interval. And then you get this tree structure because you can start with 0, 0, or you can start with 0, 2. And these are disjoint. And on the other hand, you can start with 2, 0, or you can start with 2, 2. And you see this, and there's finitely, so it's the union of finitely many disjoint closed sets that are also open. And so these are all open. And when you take in the intersection of those guys, you get a point. So the connected component of each point is just the point itself, because it does not contain any cylinder set. Okay, so this is kind of classical, but it's good to keep it in mind because, in fact, when we do random walks and groups, we are somewhat, there is a shift space in the background, which is quite useful. So let me introduce what are the fundamental sets that we are going to study in this course. So for random walks on groups application, in a sense, to random walks. Okay, so here we start, our alphabet could be actually infinite, but it's more or less the same. So we start with G, let's say a countable group. Let's discuss only this case. And mu, a probability measure on G. Well, what does it mean? Well, as an example, you can say that if the support of mu could be finite, so it could be a bunch of group elements, B1, Bs. So this would be group elements. And mu of Bi is exactly what we said before. It's like Pi. So you have a sequence, you have a vector, you have S group elements, and to each of them you associate a probability. This is not always the case, because you could also do an infinite version of this, which could be, so another example with infinite support, it also works, is like, for instance, you could say if G is Z, well, you could say that mu of K of the integer K as an element of Z is, well, let's say 0 if K is less or equal to 0, and C over K squared if K is less than 1, where C is some constant that you just choose so that the total sum of C over K squared for K bigger than 1 is 1. This, of course, can be arranged because this sequence, the series is convergent. So this is an example which is a bit slightly more general, because Now you don't have only finitely many choices, but you could have infinitely many choices. So your alphabet, so you take in general, you take your alphabet to be, well, you can even take it to be G. That's the most general case. So some of the weights could be 0, but it's not a problem, right? So you take an alphabet to the G, and then what? So your space X is the product space where you take a G to the N. So your alphabet is this. So you take sequences of group elements, and our measure is this mu to the N. And okay, the Borel sets are defined using that topology, for instance. And in any case, what you need is, and T is again the shift map. So let me expand on that, because this is a really, really important point. So an element of G and X equals Gn. Okay, we're not going to use the letter X for this set anymore, but just to keep it in the tune with what is said. But so an element of Gn is a sequence of group elements of elements of G. And basically, it corresponds to taking, so the fact that we're taking this product measure here, it corresponds to say that these GIs are identically distributed and independent of each other. So again, you have mu n, so mu n of a sequence G1, Gn, and then whatever, something. So if you have a set like this, so if you have a set of sequences that are like this, sequences G that are like this, well, the measure of that set is mu of G1, mu of G2, mu of Gn. So we take the product of the weights. So it's exactly the same as the shift map for the Bernoulli shift, but there's alphabet is just a group now. Yes? No. We haven't talked about the group structure yet. So these are just really elements of G. Now, yeah, so for instance, let's make an example, right? So if G is a free group, and we can take the support of mu to be A inverse, B, and B inverse. That still would be fine. And then you see, an element would be whatever. You could start with A, B, B inverse, A inverse, B. At the moment, we haven't done the multiplication yet. So this is the first stage. We just look at the sequences. Okay. So in fact, the definition to make sure, so the space Gn with this product measure is called the step space of the random walk. So this is only, yeah, is the very first step. We just look. So because in a way, each such thing gives you the instruction for one step of the walk, right? So if you have a sequence like that, in say the free group, this corresponds to, you do A, and then you do B, and then you do B inverse, And then you do A inverse. So clearly, you're going back to the identity, but you're recording the whole path at the moment. And then again, you do B. So this would be this element. Okay, and so again, this and so its elements are denoted by these GIs. So the notation is important. Okay, it doesn't have to be GIs. This was my notation, which was smart, but okay, other people have different notation, but it's important that there's two different spaces. So this is one space. So its elements, so in this course, I follow that notations, are denoted by Gn. And so you note that for each n, you can look at the sequence. Yeah, just Gn could be, you can think of as a random variable from this space into the group, just looking at the nth coordinate of that. So this one is a random variable. And G1, G2, Gn are all IIDs. They're all independent and identically distributed with the same measure mu, with law mu. Seems like a lot of setup for something trivial. It's another way to discuss this infinite, coin toss. But since you have to be familiar with the various notations to make sure that these things will interact with each other. Okay, this is kind of obvious. Okay, then, and what is the shift map? So what is the dynamics here? So we have the shift T in the step space again. And this is just T of Gn equals Gn plus 1. So this one is also, of course, is preserving this infinite product measure, precisely because this is a product measure, so by definition. So this shift, what does the shift does geometrically, though? This shift is a bit annoying to look at geometrically. Because geometrically, right? So if you do T of this guy, A, B, B inverse, A, inverse B, right? This corresponds to you just forget the first step and you apply the second step as if was the first one. So it's kind of complicated what it does geometrically, right? Because this would correspond to do, B inverse, A inverse, B. So it's a completely different path from this. So the good thing about this T is that it's measure preserving. Now, we need to define the other space that we're going to study. So, which is the path space. So this is where this is where all the things are happening. Yes.
Like the function Gn from.
Yeah. So you see, I have an infinite sequence, and I can take the nth entry of this infinite sequence.
Oh, okay.
That's it. So special. But you can think of this as a probability space. And so I look at, the nth increment would be a function from the space of infinite increment to the group. And you can think of it a random variable, but in the sense that it's a group valued random variables, which if you're used to it, it's nothing strange, but it could be if you're not in. Yeah. Okay, so the other space is the path space. And the path space we always denote by omega. Again, not to confuse with the step space. Okay, so as a set, omega is also the space of infinite sequences, and that's why it sometimes gets slightly confusing. But it has a completely different dynamical meaning, and yeah. So what you do is just the following. So for each, so given a sequence Gn in your path space, in a step space Gn, you define a sequence Wn, and this sequence will live in this omega. So it's another sequence of group elements by, and you define it like this, you take the product. So Wn is G1, G2, up to Gn for every n. So now you see the group structure, you do the products. Okay? And so this defines a map. This defines a map. Let's call it pi from Gn as the step space to omega. And we're going to call the omega the path space. And so here the elements are Gn's, and here the elements are Wn's. Yes?
Sorry, why is omega Gn not G?
No. Omega is still a space of infinite sequences.
But the word Wn is a word.
No, because for each n there is such a word. Yeah, for each n, so it's a space of, yeah, it's a sequence.
Oh, it's G1, G2.
Yeah, exactly. So yeah, so maybe we can give this the example as we said before. Yeah, it's a space of infinite sequences. So yeah, so again, if we start with pi, if we start with the sequence A, B, B inverse, A inverse B, and so forth, well, the first is just, so W1 is just A, W2 is AB, W3 is AB, B inverse, which is A again. And then AB, blah, blah, blah. So this would be identity. And then it's B. So this is W1, W2. Okay. And so an element Wn, so it's a sequence, is called a sample path. So this sequence records the location of the walk, not the steps, but rather the locations of the walk, right? So because if you do this sequence of increments, you go to A, then you go to AB, then you go back to A, then you go to identity, and then you go to B. So it's the same path, but it's just encoded in a different way. Okay. And now the other very important thing here is that we need a measure. So we define. So here's again the most important measure here is P, which is the push forward of mu n under this map. So we have the product measure here. So we're describing the same stochastic process, is just in a different way. So here we have the product measure. We push it forward, we get a new measure, and we just denote this measure by P. So omega P is the path space. So we'll try to keep this notation, omega and P, because, okay. And so the two remarks are that one, so its elements are, okay, they're called Wn, but are not IDs. So the I's, so the W1, W2 is not independent of W1. It's the ratio between W1 and W2 that is IID. So, and the second thing, because you can think of like the walk, you know, we'll have already made some progress at the step n. So, you know, the walk at step 100 cannot be distributed like the walk at step 1. At least, you know, if, for instance, if the walk is making some progress, right, it makes sense. And the second is, okay, the map, there is a map which you can think of as shift map, but this is the wrong shift map to think about, at least. So if you have a map S from omega, so if you have a map, you can do shift on omega. SWN is WN plus 1. Okay, this map is forgetting the first location of the walk. This map is a map that actually we will talk about, but is not measure preserving. So here's the other thing, that this space encodes the locations of the walk. It has a nice measure that we were gonna use all the time. But the way this measure works is the entries and the sequence are not IIDs anymore. And also it's possible to think about a shift map on the space omega, but this is a very different map from the other one. They don't conjugate to each other at all. And one is measure preserving, the other one is not measure preserving. So when we need a measure preserving system, we go to the step space. But the path space is useful most of the other rest of the time we're gonna use the path space. Okay, good. So maybe we can take a break since it's like 11:08. Yeah, so let's take a break until 11:15 maybe.
Hi, Professor.
Yep.
Yeah, I'm just wondering, is there a neat condition to make this this S map being to turn this into a measure preserving system? Like it seems like intuitively it's related to like reversibility of the walk.
Yeah, that's right. So yeah, in certain situations, yeah, I think this is somewhat related to the triviality of the Poisson boundary that we will see at some point. So yeah, I think in some very special cases, I think it will be, but I don't think it's just as simple as the walk being reversible. But we can try to do the computation, but yeah, because I mean, again, if this is measure preserving, sorry, if this is. Yeah, this would mean that every step of the walk, every location of the walk for any time is distributed according to the same law.
Mm.
So I think, for instance, that the walk would have to be recurrent for that to be the case. So it is somewhat unlikely, but I think it is true that in some cases it probably should be. So maybe for abelian groups or something like this, it could be actually.
Okay. Yeah.
Yeah. So one could try to do the computation, but yeah.
Yeah, thanks.
Yeah, thank you. Okay, I think we might want to get started. So okay, so now let's discuss ergodic theorems. So first of all, ergodicity, which I haven't defined yet, and ergodic theorems. So okay, so first of all, ergodicity. So ergodicity is a form of irreducibility for measurable dynamical system, and the definition is simple. So a measure preserving system, again, this is ergodic if basically for every set in A such that it's invariant, so T inverse of A equals A. So every invariant set, so the measure is always invariant, but just as a set, if this is invariant as a set, then P of A, okay, let's say that for the let's assume that probability of the whole space is 1 for simplicity, because this is what we're gonna do forever in this course, even though you can think of ergodic theory where the probability of the whole space is finite number, for instance, or even for infinite one, but that's much more complicated. So then P of A is either 0 or P of A is 1. So every invariant set for your system has either 0 measure or it has measure 1. So anything that we can say, and the idea here is anything that we can say that this is asymptotic in nature, so that you're taking certain limits over time, will tend to be invariant. And so every property that is formulated in terms of limit over time should hold either for almost every point or for no point up to a set of measures. In fact, so let's see, famous lemma is the following, that yes, so that a measure preserver system is ergodic if and only if for any f, let's say in L1, or it doesn't matter, in fact, too much what functional space you have such that, which is invariant, such that f composed with T equals f, then we have f is constant, that f is constant almost surely, almost everywhere. So this is the counterpart. So remember that we have a sort of duality between sets and functions. So on the one hand, you have invariant sets, and on the other hand, you have invariant functions. So ergodic means you really cannot split the system in two so that the invariant set, there is an invariant set that has measure 1/2 or something, which is neither 0 nor 1. And the same is true for functions. So the only functions that are invariant are the ones that are constant. Let's see some stupid examples of non-ergodic systems. Well, a system that is not ergodic could be a system that has several components. So for instance, if you have a graph that has several components, like some market chain like this, for instance, or even like that. So if you have a system that has, okay, you can produce the correct invariant measure for this, you can introduce some probability of going along the edges. I don't know, 1/2, 1/2. This has to be 1 and something. Yeah, whatever. Okay, this is not so complicated. You can make more complicated systems, but basically, if you start from here, you either end up in this component or you end up in this component. So it means that if you have this set is invariant under time evolution, but it has measure which is a fraction, like say maybe 1/2 or some positive fraction of the mass. So this is what we don't want. So ergodicity is some sort of irreducibility. I guess the most famous lemma in this system is that the map T of x equals x plus alpha for alpha irrational is ergodic on S1 with the Lebesgue measure. So if we take an irrational rotation, so first of all, a rational rotation, yeah, let's see. I see another counterexample. So suppose you do T of x equals x plus 1/2. Is this ergodic? Mod 1. Yeah, on a circle, yeah. Can you find an invariant set that does not have full measure? Yeah.
Like this, where you got,
Yeah, that's right. So if you take some set like this, when you rotate by half turn, the two pieces swap. So this set A is invariant. So the inverse of A is A. But the probability, the measure of A, well, it depends on how you choose it. But let's say this is Lebesgue measure. Well, it is neither 0 nor 1. You can choose to be, I don't know, 1/2 if you choose it completely symmetric or whatever. So in fact, here there are really a lot of invariant sets that are neither 0 measure nor full measure. But if you do an irrational rotation, then this one is ergodic. And the best way to do this is to check using functions. So okay, so we have to prove the lemma here. And also we have to prove that one. Okay. So let's see. So suppose that the measure preserving system is ergodic. Okay. And then we want to say, and suppose that we have a function that is invariant. So we want to show that this function is constant. How do we show that? We want to show that f is constant. Almost surely. So we have, you see, we have some property about invariant sets, but now we have an invariant function. How do we construct the set from the function? Yeah. That would work, but it's not so useful because the preimage of a singleton most likely will have measure 0. Yeah, but if you have a normal, like most functions that you dealt with in calculus, right? For every singleton, the preimage of a singleton would be some finite set of points, so it would have 0 measure. It would be correct, it would be invariant, but it's not quite enough. But it's more or less the right idea. What's the right set? Yes. Of what?
the set that you want to show.
No, you don't want to show. Yeah, that's the other direction. So here we're saying we have we have an ergodic system and we have a function. So we have to produce a set.
Oh, right.
Yes. So what you're saying is correct. So exactly. So we can look at A to be the set of X such f of X is, say, bigger or equal to some constant C. Right? And now we want to prove that that is indeed invariant. Yeah. And so that's kind of like that. So you have, what is T inverse of A? Well, it's a set of X such that f of Tx bigger than C. But depth composed with T is F. So this is the same as X times the F of X. And so this is A. And so what do we know? We know that the measure of T of A is either 0 or 1. And this is true for any C. So now you have a function that if I look at the sub-level sets or super level set, then for every sub-level set, the measure is either 0 or 1. So now why is this function constant almost everywhere? Right? So if we take C, suppose, if we take C to be minus 1,000,000, this set will be very large. Because it's very easy for a function to be bigger than minus 1,000,000. Now, if you take 0, well, the set will be smaller, right? And so we take, so at some point, there has to be jump, you see? Because it cannot be, so suppose that, okay, the sublevels, the set where F is bigger than minus 1,000,000 has probability 1. And then it's still 1, 1, 1, 1, 1, 1. Can it be 1 forever? Now, it cannot be 1 forever. Otherwise, the function will be bigger than any constant for every point. So this is not a function. Right? So we define I don't know, some constant. What's your favorite name for a constant? Let's say K. Yeah, so this would be what? It would be the supremum of the set of C's such that the probability that F of X is bigger than C is 1, I think. Yeah, right? Because if so this sets, right? If C is very small, the set is 1. So it's 1, 1, 1, 1, 1, and at some point it becomes 0. So you take the highest value such that this is 1, and then then you can check that F equals K on a set of measure 1. Of measure 1. So here's another good trick. Take the sub-level sets. This is always a good trick. Okay, and how about the opposite? So if F, suppose that, right, suppose that A, you have A equals T inverse of A. Okay? And we know that every invariant function is constant. How do we show that? So we know that every T invariant F is constant. We want to show that the probability of A is either 0 or 1. So now from set, we have to go to function. And what's the standard way to go from a set to a function? Yeah, you take the characteristic function. And so you take, so the trick is to take function as 1A. And you can easily check that since A is invariant, the characteristic function of an invariant set is an invariant function. And so since it's an invariant function, it has to be constant. So the characteristic function has measure as probability. Yeah. So, sorry. So it's a constant. And so, right. So it could be constant. So a characteristic function has two values, either 0 or 1. Right? So if it's constant, almost surely it's either constant equal to 0 or constant equals to 1. Right? So you can have F equals to 0. This means the probability of A is 0, or F constant equal to 1. Then the probability of A is 1. So that's pretty pretty standard, but it's nice too. Also, let's look at the fact that L1 here is not really necessary. We could also replace with L2. Yeah, or even just measurable. I mean, the issue is just that we want that this characteristic functions are inside this this class of functions that we're looking. Yeah, so why do I say this? Because to prove this lemma, I think the correct thing to do is to take f in L2. So what do I want to show? I want to show that if you take an irrational rotation on the torus, on the circle, you get an ergodic system. So the proof is like this. So you take f in L2 of S1 with respect to the Lebesgue measure, and we assume that f composed with t equals f. And now we want to show that f is constant, almost surely. So how do we do it? There are several proofs, but the most elegant one usually is using Fourier series. Because you see, f is a function on a circle, so it's a periodic function on the real line. So you can write write in Fourier expansion. So what's the Fourier expansion? Well, f of x is the sum over n in z of some coefficients an times e to the 2 pi I n x. So in L2 of the circle, our function on the L2 of the circle can be written like this, where equality is in L2. And an is in small L2. And then we can check really easily the invariance. Why can we check the invariance? So f composed with t of x. So the map t is x plus alpha. So we can just write. So this is sum on n over z of an e to the 2 pi I n x plus alpha. Again, this map is defined almost surely. So it's not true for every point, but certainly for a full measure set of points. And this also is a Fourier representation almost. This, we can write it like that, is an e to the 2 pi I n alpha times e to the 2 pi I n x. So this changes the coefficients in the Fourier expansion. And we know by what we said before, this has to be the same as n in z of an e to the 2 pi I and x. And now if two functions have the same Fourier representation, two functions are the same, they have to have the same Fourier coefficients. I mean, you can also write Fourier coefficients as the, integral with respect to the conjugate character, whatever. But yeah, so the upshot is that this coefficient has to be the same as this one. So for every n, an has to be equal to an e to the 2 pi I and alpha. So can that be true? Well, you can rewrite this as an times 1 minus e to the 2 pi I and alpha equals 0. So can this be true? Well, this is that either an equals 0 or, well, e to the 2 pi I n alpha has to be equals to 1. But can that be the case? E to the 2 pi n alpha equals 1. So can this be the case? Well, it depends on n. So since alpha is irrational, so for every n, for n equals 0 is true, e to the 0 is 1. Right? So since alpha is irrational, this implies yields right that, yeah, so e to the 2 pi I and alpha different from 1 for every n different from 0. And so an equals 0 for every n different from 0. So it's important because you cannot have a function where all the Fourier coefficients are 0. This would be too much to us. Where you can have that all coefficients except the 0 coefficient. Right? And so this would imply that f of x is just a 0, so this is constant. So it just literally is perfectly fine. Because this issue here is this is a group translation, and you have a nice Fourier series for this group. I mean, in general, you don't. So that technique is kind of not applicable very often, but in this case. Okay, so now that we saw the very basics of ergodicity, so we can look at the very basic ergodic theorems.
Is this true for every map that the map on a circle is ergodic only if the Fourier series is just constant term?
For what function? So here's so depending on what is T of x, right? So what is good here is that T of x is x plus alpha.
Right.
Now, if you do T of x, actually, I should have put this one as one of the exercises too. This is a very nice exercise. If T of x is 2 times x, the approach using Fourier series still works, but it's a bit more complicated because you still have a nice way of expressing this function in the Fourier series. Right. But yeah, but of course, if the map is, I don't know, if you have a Möbius transformation acting on the circle, then you cannot apply this, at least not easily here. Yeah.
So we put a lemma for like all one function. So if you want to apply lemma, it means like a density argument.
Yeah, that's what I was saying. Yeah, so this is true for L2.
Yeah.
And but the same argument that we gave for L1 is literally the same for L2. So you could add another small lemma there. Yeah. No, you're right. Yeah. Okay, very good. So okay, so in terms of ergodic, so what are ergodic theorems? So ergodic theorems are theorems that tell you that some sort of average exists. So averaging is a good thing in math. And whenever you have some quantity, you don't know what to do with it, you try to do the average first, and maybe it's better. So averaging works. This is the upshot of ergodic theorems. And there are several with different names. So basically, okay, so the tech sort of historically, the first one is due to von Neumann. Then the most famous one is the one due to Birkhoff. And in fact, historically, there is a very interesting sociological and story here, because somehow it looks like, and so there's some papers about this, Birkhoff didn't want to publish von Neumann's result. Yeah, he was a bit of an anti-Semite, actually, and he didn't want to publish von Neumann's result, and he came up with his own theorem, which is better. And then eventually they published And they published it in the same volume, but von Neumann came up with the first of them, even though it's the least general. And then later there's Kingman's. So, and then, well, in many ways, you can say the martingale convergence theorem is also some sort of ergodic theorem, even though it's not quite formulated like it, but it still tells you that some convergence exists. So, and it's quite similar in spirit. So this would be the fourth one still. So the von Neumann theorem is in L2. Birkhoff is in L1. And those are for additive processes. So I'll define exactly what it means. But this is for additive cycles. And then this is in L1, but it's only just for sub-additive processes. So this is more general. And in fact, we will use it a lot in this course. And then the martingale convergence theorem, well, is for another type of process, which is, of course, a martingale, which is not quite a subadditive co-cycle, but again, it has some close similarities to it. Yeah. Okay, so maybe let's start formulating the theorems. So let's look at the first generation of ergodic theorems due to von Neumann and Birkhoff. So what is the idea? Again, remember, so you start, let's say F start is an L2 of XP. So this is a measure preserving system. So, and we have T from X to X is a measure preserving. So remember that we have special type of function, which is invariant functions. So invariant functions are very important. L2, let's call it L2 XP T. So these are functions in L2 that are invariant under these dynamics. So these are very important ones. The constant ones, of course, are some such, and sometimes there's more than those. So the ergodic theorem tells you how to produce an invariant function starting from any function. And the idea is you do an averaging procedure. So we define, in fact, this is called usually Birkhoff sum or ergodic sum. Ergodic sum is the following. So you take f of x and we apply the dynamics to it. So f of t of x and f of t square of x and so forth. So f t n minus 1 of x. So this is a sum over the first orbit, first n orbit. So let's call it this SNF of x. Again, for this to exist, f need not be in L2, it could be in L1, it could be any measurable function. Right? So you just take the sum over the first n iterates of this observable. So remember, f is something like the temperature, and you're taking the temperature in n consecutive days in the same location. And you're taking the sum. Okay. So here's the theorems. So the theorem of von Neumann is the following. So there exists some f bar in L2 of XP such that, it's invariant. And if you take SNF divided by n, converges to f bar in L2. So this is the first way to get an average. You take a function, you apply the dynamics n times, you do the arithmetic average, and this converges to a function. The limit exists. And in von Neumann's time, this was the limit in L. So some sort of averaging. So over, yeah. Now then, what, F bar? Yeah. Yeah, the limit exists. So it's like, so for each F, there is.
So not passing to a subsequence, right?
No, exactly. There's no passing to subsequence. That's right.
But F does not have to be in that state,
right? Yeah. So you start with let F, let F to be in L2. That's right. And T is the measure preserving. Yeah. So now the theory of Birkhoff is is very similar, but more powerful in the way the convergence works. So this is for L1. So let F in L1. First of all, again, T is the same, the measure preserving system. Then there exists, again, F bar in L1, such that, well, F bar composed with T equals F bar. And, okay, the convergence is stronger. So Sn F of X divided by N converges to F bar of X. Well, not just in L2, but actually in L1, but not just that. The really important and strong property is this converges for almost every, for P, almost every X. So it's an almost sure convergence. In fact, and in L1, but okay, this is not so big of a deal. So the reason why the second formulation is indeed way stronger in the sense of whenever we're going to apply almost always this version, because this is way stronger, is because this is for almost every point. So you see, so it means that there is a full measure set of starting points where you can really take the average. The infinite average exists, and this gives you this new function. Okay, and so so let me first add some remarks. Then we might go to Kingman's theorem and so forth. But okay, let me add some remarks. So I actually like von Neumann's formulation because it has a very nice functional analytic aspect to it, because you can think of the following. So you can think of the space of L2 functions is some Hilbert space. So this is L2. And then the space of invariant functions is the subspace of it, right? So this is L2T. So these are invariant functions. It's a closed subspace. Could be one-dimensional or more. And the ergodic theorem, basically what it does is it takes a projection from the space F is a let's say this is the 0. F is a vector in this Hilbert space, and it gives you the projection So F bar is the projection of F to the space of T invariant. It is, I agree. So the remark is the following: is that F bar is the projection, the orthogonal projection, so to speak, the closest point projection, basically, from F to the space of invariant functions. So I think this is a real cool fact. So in fact, okay, I can give you an idea of von Neumann's proof, just because I think it's cool, like just how to think about it. Eventually, we're gonna do the proof of Kingman's theorem in full generality, which includes both of those. So, but that is kind of technical as well. So maybe let's say the idea of proof for the von Neumann ergodic theorem. And the idea is the following. So let's think of the following subset C of functions that can be written as G minus G composed with T for G in L2. So some functions are written as the difference of G and the G composed with dynamics. Okay, so this is a subset, some subspace actually of L2. So these are not invariant functions. Then there are invariant functions. So these are too easy, sort of nice. So the claim is the following: is that if you start with the space L2, this is the orthogonal. Yeah, is the union, is the, you take the closure of this, and this is an orthogonal sum, so it's with the invariant functions. So basically, there are invariant functions such that f equals f composed with t. And there are these other strange functions that are so-called co-boundaries. It's like G minus G. Not exactly like that, but if you take the closure of that, you get all the functions. Okay? So this is not obvious, but okay, it's a neat proof. But then, okay, now once you have that, then it's easy to check that for f in C, well, S and F with divided by n, well, this one converges to 0. And why is that? Well, because you can telescope the series, right? So this is what? This is 1 over n sum of f composed with t to the k equals 0 to n minus 1. This is one of my favorite tricks that I always like. And now, if f is g minus g composed with t, this is the sum of g composed with t to the k minus g composed t to the k plus 1. And then this is telescoping. So you just have 1 over n g minus g composed with t to the n. And so the norm in the L2 norm of this clearly is going to 0, because this is bounded by the norm of g twice the norm of g divided by n. So this goes to 0 in L2. On the other hand, if f is already invariant, well, what happens if you do the ergodic average of an invariant function? Well, you can easily see, right? So this is 1 over n sum of f composed with tk. But f composed with tk is f. So this is just f. Okay. So the upshot is, so in this case, you have that f bar equals f. If you start when you're already on the, so this projection that you're trying to construct, it's already the identity on this invariant subspace. And if you're taking the orthogonal complement to L2T, these functions are almost of this form. So if they are literally of this form, you just do computation. yeah, so now what needs to be checked yet is indeed that this is sort of the slightly hardest part. It's not very hard, to be honest, but if to say that every function can be decomposed like this. And once you have that, then you see that you can just apply the ergodic average on this substrate and on this subset, and you just take the sum and you get exactly what you have. Actually, let me say one more word about this operator theoretic or functional analytic way to think about this is that you can define what's called the Koopman operator, which is a bit of a fancy name for something kind of simple, is the following. UF is just F composed with T. And so this is, in fact, is a unitary on L2. Just because UF, UG, by the measure preserving nature of it, is FG. Because this is the integral of F composed with T, G composed with T, dP, which is the same by changing variables as FG dP. So in fact, this type of proof of taking an average works for every unitary operator, blah, blah, blah. So this goes to some other type of math, but it's kind of neat. On the other hand, we're going to go more deeply into the sort of ergodic theory, proper ergodic theoretic methods, which are, which are not so nice from the functional analytic perspective, but still.
Sorry, F and G are T variables?
No, but the measure is preserved. So it's not on the nose, but it's when you take the integral. Okay, yeah, I think we've done plenty of stuff today, so we can stop. As I said, so the homework is posted on the Fields portal. So you need to be registered on the Fields portal to do it. If you want a copy for your own sake, you can just ask me. And if you have trouble registering for the Fields portal, let me know. But I think many people are, and otherwise I can tell the guy to add your name. Yeah, the due date is next week. Yeah, thank you. So, yeah. It's not a very long one. Yes. No, there will be more. There will be, I think, three assignments. But these are not. Yeah, this is just the introductory stuff. So don't worry too much about the assignments, but do give it a try. Yes. Okay, good. Any more questions?
You will add us on the lesson.
Yeah, I think many people are already there, but if you're not there, you send me an email and I will give your name to the guy.
But we are.
Yeah. Okay.